Hello and welcome to the part 3 of module 5, and in this part we will be dealing with reasoning on owl ontology. Right. Now whenever we talk about reasoning, we are trying to come up with certain answers to the queries that we are posing to the ontology, or maybe from the explicitly specified facts or knowledge in the owl ontology, we will like to come up with some inferred knowledge, right? So this is the kind of objective that we have as far as the reasoning is concerned. Now when we talk about reasoning with owl ontology, and as we have seen earlier that an owl ontology can be translated into different families of description logic. So basically the reasoning algorithms that we will be dealing with, they will be working on the description logic. So basically, though we are talking about reasoning with owl ontology, one owl ontology can be translated into uh, the corresponding description logic form. And what does this description logic form will contain? It will be containing a T box, one R box, and one A box, right? And depending on the family which can be aligned to the given ontology, so we'll be having different algorithms, right? So we'll be talking about algorithms that will concern different description logic families. So that is the kind of basic objective that we have for this particular part. But before going to that, so we'll be having a generic section which will talk about different terminologies or concepts related to reasoning with description logic in general, right? So there will be a generic part. So introduction to, so that we will call as introduction to reasoning with DL, right? So here we will be talking about some generic terminologies that we are going to use for the subsequent part, and thus in the subsequent part of this particular session we will be talking about uh, DL family based inference algorithm. So this is the kind of particular plan will be. So let us now focus on this part, the introduction to reasoning with DL. There we will be talking about very generic concepts about reasoning with description logic ontology, right? So the first thing that we like to discuss about reasoning with DL in general is semantic consequence of a T box. So this is the first thing that we are going to define. Semantic consequence of a T box. So basically, after someone has defined a T box, so T box is what? So T box is basically a set of class inclusion axioms, right? And we need to see what are the kind of consequences that we can have out of an existing T box, right? So what are the kind of other things that can be entailed from this explicitly mentioned T box? So that is what we call a semantic consequence of a T box, right? So before going to that, let us define something called uh, mm, that a particular interpretation is a kind of model of a particular axiom. So let us consider that we have an axiom, right? Now if, so let us try to define something like a particular interpretation. A particular interpretation models one axiom. So this T is not to be confused with the top concept. So this T is kind of one axiom, a GCI belonging to the T box T. So here this calligraphic T is the T box, and this particular T is one GCI in the T box T. So this is the convention that we will be following. And this I is an interpretation, is one interpretation, and here we say that this I is a model of T, right? So when do we say that? If T becomes true, if T becomes true for the interpretation I. So then we say that I models T, right? Now if an interpretation, so if an interpretation I satisfies all the axioms in the T box T, basically we represent this as interpretation I models the T box T, right? So if an interpretation satisfies all the axioms in T, then we say that, so it satisfies, let me rephrase it in a different, so it satisfies all the T such that this T belongs to the T box, right? And if it is true for all the axioms in the T box, and this I is a model of each of these T, right? Then we say that this interpretation is a model of uh, this T box T, right? Now we define that an axiom T is a semantic consequence of a T box. So we are trying to say that an axiom T is a semantic consequence of a T box T, and we represent that as T models this T, right? And this T is a something, let us represent this with a different symbol. Let's say T1, and this T1 was not there inside this T box, right? So if we say that this T box models or models this particular axiom T1 if and only if T1 is satisfied by all the models of the T box T, right? Then we say that this T box models T1, or T1 is a semantic consequence of this T box T, right? So what we are trying to say mathematically, so we say that a T box models a, uh, an axiom T1, if and only if for all the interpretation, I, let's take any interpretation I, if I is a model of this T box T, that implies that I is also a model of T1, right? So in that case, we say that this T1 is a semantic consequence of a T box T, right? Uh, Now let us define something else, that two T boxes. So first define something called semantic consequence of two T boxes. Here we have taken this T1 to be one axiom, and that becomes to be a semantic consequence of a T box. Now here we are defining something else. We are extending it to the T box level, right? So we say a T box T2 is a semantic consequence of another T box T1, right? Then semantic consequence of the T box T1. So here you can see that T1 and T2 both are T boxes, but in the earlier case, T was this was the T box. This first one was the T box, but the second one is an axiom, right? So when it will happen, so how do we write this? We represent this something like this. So T1 models T2. So T2, T box T2 is a semantic consequence of the T box T1. If and only if and only if we have T1 models T for every T belonging to T2. So what we have in T1, so this T1 is a T box, right? So in this T1 we have uh, many axioms, right? So for example, T1, 1, T1, 2, so and so forth, right? Now in T2 we have got other axioms. So for example, T21, T22, so and so forth, right? Now if you see that, so for every uh, T belonging to this T2, like say T21, if this is a semantic consequence of the T1 T box, how do we write that? We write that like this. So T1 is a semantic consequence of T21. So T21 is a semantic consequence of T1, and T22 is also a semantic consequence of T1, and you have this for all the axioms that you have under T2 T box. If that is so, then we say that T1 models T2, or T2 is a semantic consequence of T1, right? Now, with this definition, let us try to define equivalence of two T boxes. Now, how do you define equivalence of two T boxes? Now, the two T boxes, T1 and T2, T1 is equivalent to T box T2, right? So basically, T1 is equivalent to T2 when will this happen? If T1 models T2 and T2 models T1. So it is similar to defining equivalence of two classes, the C and D, which happens when C is a subclass of D and D is a subclass of C. So we have a similar kind of thing, right? We have extended this into the T box level, right? Now, after this, we can define another terminology, which is the equivalence of two axioms, right? Uh, Now, when do we say that two axioms are equivalent? So, we are defining equivalence of two axioms, basically T1 and T2. So, when will this happen? This will happen if this T1 and T2, they have got the same interpretation, right? So, if you have one interpretation which models T1 and you have this same interpretation which models T2. So, if you have, so for all the models for which T1 is satisfied, then if you have for all those models, if T2 is satisfied, then we say this T1 and T2, these two axioms are equivalent with each other, right? So, with this definition, let us try to reinforce these definitions with some examples, right? So, the first example that we want to exhibit is the demonstration of an interpretation models a T box. So, this is the case where an interpretation that is a model of the T box T, right? So, let us consider our T box T1. It contains three axioms. The first axiom is we are defining the class doctor, right? The doctor class is equivalent to not animal and there exists and this doctor has treated at least one thing, right? So, this is the definition of a doctor, and let us name this to be T11 axiom, right? So, let us now define a veterinarian. Veterinarian, right? So, the veterinarian is a doctor and also it treats all the things that are animals, right? So, all that it treats are animals. So, has treated animal, and let us name this to be T12. So, this is our T11, this is our T12. And the third axiom that we have, again we are telling something about veterinarian, which is a subclass of healthy. So, veterinarian is healthy or has treated something that is healthy, right? And let us name this to be T1 thing, right? Now let us try to think of one interpretation which is a kind of model of this T box, right? T1. So let us think our domain. Now, when we define the interpretation, we need to define two things, right? One is delta and other is the interpretation function, right? So our delta, let us take this to be, say, Bob, then Tom, then Jerry, we can have Alex, and say Kiera. So this is our domain of discourse, right? Now we have got some class which is called animals, right? So let us see what would be the interpretation of animal. We are now defining the interpretation function, and this interpretation function, when is acting over this animal class, it can contain, say, Tom and Jerry. So this is one interpretation that I am coming up with, but there might be multiple interpretations, right? Now we need to talk about, say, has treated. Now has, the kind of interpretation that we have has treated, let us assume that it is containing the relations that Alex has treated Tom and Bob has treated, say, Jerry, and Bob has treated Kiera, right? And say Alex has treated Jerry. So these are the kind of ordered pairs that are there as the interpretation of has treated, right? Now let us define healthy, the interpretation of healthy, to be say Alex and say Jerry and Kiera, right? An interpretation of doctor is, say, Alex and Bob. And finally, interpretation of veterinarian is having some, say, Alex. Now we need to check whether this interpretation I, so this is the interpretation I, and this is the T box T1, whether I models T1 or not, right? Now we have, let us now check doctor, the definition of a doctor, right? So definition of doctor says that doctor is something that is not animal. So the not animal will come to be Bob, Alex and Kiera, right? And then it has treated at least one. So let us see who are the member of this has treated one. So Alex is a member of has treated at least one. Bob is a member of has treated one. I think these are the two instances that are a member of this has treated one. So what is doctor coming to be? Doctor is coming to be say Bob, then Alex and Kiera. An intersection, the set intersection of and has treated top, it will be evaluated to be, so it will contain the individuals to be Alex, because Alex has treated at least once and Bob has treated at least one, right? So if we take this intersection, we will be having Bob and Alex to be the instances of doctor, right? Which is exactly we have done, right? So it is matching with our interpretation, right? Now let us take the case of veterinarian, right? So the veterinarian is a doctor, so and something that has treated only animals. Now here we can see that Alex has treated Tom. Tom is an animal. Alex has treated Jerry. Jerry is an animal. So in that case, this uh, this for all has treated animal will be having individual. So for all has treated animal will have individual to be Alex, right? Now let us check Bob. Bob has treated Jerry. So Jerry is an animal and Bob has treated Kiara, but Kiara is not an animal. So there is at least one instance which Bob has treated but does not belong to animal class. So that's why Bob will not be there in our uh, set of all has treated animal, right? Now, the veterinarian, what it will include? So this vet, it will include the set of doctor was Alex, Bob, and intersection Alex, right? And if it compute this, it will be becoming to Alex. And you see that the same interpretation we have here, right? So you see that all the this interpretation goes well with this T box. So that's why we say that this interpretation I is a model of T1, right? So this is what we have demonstrated, right? Now the second case that we will try to demonstrate is the fact that T box, one T box, one T box has a semantic consequence to be one axiom. So the axiom T is a semantic consequence of the T box T, right? Now let us consider the T box T to be, say, we are defining mother of scientists, mother of scientists, right? Now let us define this to be equivalent to not male because we are defining mother, and all the child this thing or this entity will have, they are all scientists as child scientists. And also we are putting a closure on this by saying that it will be having at least one child, otherwise the person may not be a mother. So at least has got at least one child, right? So this is the kind of uh, T box, the axiom that we have in the T box, right? Now let us consider the axiom T to be uh, this to be, so this T we are defining to be not of male, right, and mother of scientists, and the intersection evaluates to be null or nothing, right? So we need to check whether this models this or this T, this axiom T is a semantic consequence of T. Of course it is, because this, so our T is not this. This is our T, right? So of course, this will be a kind of consequence of this, because uh, when we define mother of scientist is not a male. Now we are taking that to be uh, conjoined with male. So you have male, we have a situation like male and not of male, and of course it will evaluate to be none, right? And that is the kind of axiom that we have for T, and we can safely say that this T entails the axiom that we have here, right? So if this is true, then this is also true. So this is how we'll be saying, right? So we have demonstrated what do we mean by an axiom to be a semantic consequence of one T box, right? Now we'll be talking about the third case, which is basically the equivalence of two T boxes, right? And when we define this equivalence, basically we are trying to see whether T1 uh, models T2 and T2 models T sorry T1, right? So basically here we are also taking the case of one T box is semantic consequence of another T box. So in the same example, we are demonstrating equivalence of two T boxes, and also we are demonstrating that one T box models another T box, right? So for this, we'll be taking into account this earlier T box that we have defined, and we name that as T1. So this will be acting as our T1, and we have another T box which is basically T2. So let me define T2 first, right? So T2 is having the same set of axioms except the last one. So we'll be having the first two axioms to be same. So doctor is equivalent to not animal and has treated at least once. And let us name this to be T21, right? And again we have the same definition of veterinarian, which is basically equivalent to doctor and for all has treated animal. And let us name this to be say T2. But the third one is something different than the first one. So the third axiom that we have, again doctor, and doctor is a subclass of something healthy union there exists has treated healthy union not animal, and this is our T23. So you see these two T boxes T1 and T2, they have the same set of axioms. The first two axioms are same, but the third one is different, right? And that has been done intentionally to show or to demonstrate this thing. So T1 entails T2 or T2 entails T1. If we can show both these things, then we can establish that these two things are equivalent with each other, right? So so what would be our uh, static, right? So you see, whenever you are trying to find out whether T1 models T2. Now, as we have the first two axioms to be the same, basically this will boil down to proving whether T1 models T1 3, sorry, T 2 3, because these two are common. So the first two are common, but the last one is different. So if we can show that this T box T1 models T2 3, so I need to be careful while I am using this symbol, so it will be simple T, right? So if you see that T1, the T box T1 models T2 3, then this will be established because of the very fact that the other two uh, axioms T21 and T22, they are kind of same, they are intent already, right? Now coming to the other part, which is T box T2 entails T box T1, right? So this we can simplify to say that T2 models T13. So if we can establish this, then we can prove, if we establish these two both, we can prove that T1 is equivalent to T2. So that is what we are going to do, right? So let us first look at the case of proving this. T2 models T13, right? So the one direction of proof, one direction of proof, which is basically T2 models T13, right? Now, so for this, we will be considering any arbitrary interpretation. So when this will be happening, so for all the interpretation which are kind of model of this T box T2, they are also model of T13. If we can prove that, then our job is done, right? So for that, let us consider any arbitrary interpretation, right? So let us consider any arbitrary interpretation, say I, and that in that interpretation there is an individual A belonging to delta, right? So it is in that, in I. So this is an I A which is belonging to delta, and this delta belongs to, right? Now, so what is your T13? Let us try to write it down, then we will go forward. So T13 is veterinarian, is a subclass of healthy union or disjunction. Their excess has treated healthy, right? Now let us assume this veterinarian A holds. So we are making A to be the member of veterinarian, right? So if that is so, then as a conclusion, we should get that A is a member of this class also, because we are having a class subclass relationship. So if we replace veterinarian to be say V, and this next part to be something say C, then everything, every individual that is a member of V also a member of C, right? So this is what we know, and if we can prove that A is a member of this class expression, then our job is done, right? Then this entire expression will become true, right? So we got to prove prove that A is a member of this class expression. A is a member of this class expression. So this is the kind of proof we need to get, right? Now let us try to go forward with this. So we know that this, so we'll be writing vet in place of veterinarian, right, to save time. So we know this is true, right? And in T2, let us go to T2. We have something called, we will be making use of this, right? Now if you make use of this too, then A will also be a member of doctor, because A is a member of veterinarian, right? So from this fact and T22, we can infer, and this is entail, that A is also a doctor, right? Because of the fact that if something is a veterinarian, that is also a doctor and plus something, right? But the first thing is that it should be a member of doctor, right? Now after doing so, let us go to the definition of doctor here, right? If something is a doctor, that something is a member of this entire class expression, right? So we can make use of T23. Now if you make use of this too, so we can make this A to be member of the right hand side of this T23. And what is the right hand side? Healthy, disjunction has treated, healthy, union, not animal. So we will derive healthy, union, has treated, healthy, disjunction, not animal. So this is the right hand side of T23, right? And A would be a member of this, right? Because we know that doctor A is true. As the right hand side is, A is a member of the right hand side, A should be a member of the left hand side, it should be a member of the right hand side, right? Now as we arrive here, now we have got two choices. Either A is a member of healthy, or A is a member of this complex class expression, right? So now we have a bifurcation, but this bifurcation should be treated in a sense of or, disjunction, right? So it is either healthy, A is either healthy, or so let me put it somewhere here, right? So A is a member of, has treated. We are doing very intuitive logical reasoning, right? Healthy, animal, and A would be a member, right? Now with this, what we can infer? So if we look at T22, so let us go to T22 and try to combine that with veterinarian, right? Now if veterinarian A is true, then A is a doctor, which we have already considered, and also A is a member of has treated animal, right? That is what we can get. We are trying to combine vet A, which we know to be true, we have asserted to be true earlier, and we are trying to combine that with T22, right? And from this, what we can obtain? We can obtain this thing, and also we can obtain that A is a member of for all has treated animal A to be a member of this, right? Now, if we try to combine this with this, right? So it is saying that whatever whatever A treats is an animal, right? Now here we are saying that A has treated at least one thing that is either healthy or not animal. But as A treats all the things that are animal, so this not animal thing will become false. So this path will not take, and by force we need to make this to be true, right? So as by force we are making this to be true because we are trying to combine this and this. In one sense we are saying that A treats all the things that are animals. But here we are having two options. One is A treats either something that is healthy or A treats something that is not animal. But as A does not treat any non-animal thing, so this thing will go away. So this will not go with the this will not be consistent with the kind of logic reasoning that we are having or facts that we have derived, right? So only thing that will be true here if we combine these two is their excess has treated healthy, right? And A is a member of this. Now you see we have one membership of A here. A is a member of healthy and A is a member of has treated healthy, right? But they are uh, joined with one disjunction. They are in a disjunctive path. So that's why if we try to recombine this two, this will get us healthy union their excess has treated healthy and A to be member of it. And exactly this is the thing that we are trying to prove, right? So we have proven that if A is a member of veterinarian, then A is also a member of the class healthy union their excess has treated healthy. So this is what we have proven, and we have already proven the this kind of consequence that T13 is a consequence of T2 T box. And if we do so, we are really saying that T2 models the T box T1, or T box T1 is a semantic consequence of T2. So this is we have proven, right? Now let us work on the other part, right? So the other part of the proof is basically trying to say that we have to prove that T1 is a model of T23, right? So what we have in our T23, let us go back. In T23, we have doctor is a subclass of healthy union uh, uh, has treated healthy not animal, right? So our T23 our T23 is doctor is a subclass of healthy union their excess has treated healthy union, not animal, right? So again, we'll be doing the same thing. Let us assume that there is one arbitrary interpretation which is a kind of model of T1, and so we have one arbitrary interpretation I, which is a model of T1, and in that I we have one individual A belonging to the delta I, right? And let us assume that Dr. A holds, right? And we got to prove that uh, healthy union, their excess has treated healthy union or disjunction animal, and A is a member of this group, right? So this is why what we got to prove, right? So how do we start really, right? So from T12, if we take T12, so what is T12? T12 says that we are flipping the sides, and that will cause no harm. Doctor for all has treated animal we are writing vet in place of veterinarian, right? Now what we are doing, we will be adding a disjunction of not of this in both the sides, right? So doctor intersection union has treated animal disjunction not of for all has treated. We are trying to eliminate this. We are trying to eliminate this part, right? So not of for all has treated animal. We are adding this disjunction in the both the sides. That we can do, right? That will keep this equation balanced. Not of, so yeah, not of for all has treated animal, right? Now if we consider these two, this will evaluate to be true because it is like you are taking C disjunction not of C, and this will always be this, right? And if you take intersection of this with doctor, it will always become doctor, right? So the left hand side with will be simplified to derive doctor, right? The right hand side will become vet uh, disjunction not of for all has treated animal, right? Now we'll be using this to combine with other things, right? Now let us look at T13, right? So what is our T13? T13 is we are defining a weight to be the subclass of uh, healthy union has treated healthy, right? So we are trying to conjoin this with the uh, so basically we can simplify this like, let me simplify this more, that will give us advantage. So wait, we just push this negation inward. If we push this negation inward, we will be having there exists as treated not of animal, right? Now we make use of T13. And what is the form of T13? T13 is a form like weight is a subclass of something, right? Now if we replace this weight by this, then the entire thing, this doctor, will become a subclass of the replacement and the remaining part, right? So if we try to combine these two, then what we'll get? We'll get doctor to be a subclass of healthy union, not of there exists as treated healthy. So this is what we have got, and union. So here, so this is the second right hand side of T1. So we have done that. Then what we have? We have this part left, right? So there exists as treated not of animal, right? Now if we try to make this simplified, so this doctor will be a subclass of healthy union. We can now simplify this to say has treated healthy union not of animal, right? Now what we have? We have assumed that Dr. A holds. Dr. A holds. Now if we combine these two, then A will become the member of this as treated healthy union not animal, and A will be a member of this, which was the kind of thing that we was to prove, and that we have proven, right? So we have proven that T1 models T23, right? And in that sense, we can say that T1 models T2. Earlier we have proven that T2 models the T box T1, and if we combine these two, we can say that T1 is equivalent the T box T2. So this is how we can prove that two T boxes are equivalent to each other, right? So with this, let me stop here, and in the next video lecture we'll be starting we'll start discussing on different reasoning tasks concerning the T boxes.